Okay, we have seen how to compute the distributions of functions of random variables. As I said, you can use any method that appeals to you, whichever you find easier. You can use the law of total probability, or if you can see the boundaries easier, you can, instead of conditioning, you can just work with different domains, whichever is easier. It just depends on the nature of the function g. Okay. Next, we will look at the moments of functions of a random variable. And here we will first of all consider a discrete random variable and then we will generalize this to continuous distributions. And y is defined, the random variable y, as the function g of x for some function g. To compute the expected value of y, we will just apply the definition. Assuming that you have the distribution of y, the PMF of y, we can write this as this expression. For any outcome that y can have, just multiply the outcome with the corresponding probability and add them all up, which can be expressed like this in an expanded form. But when you look at each term, y1 times the PMF of y at y1, this is nothing but the probability that random variable y takes the value y1, okay? And y1 is what? It's the function g applied to some x1, okay? So here, y1 times this probability, but this probability is, as I said, nothing but the probability of the event g of x is equal to y1. So for all possible x values that give me y1 when applied to g, just add the PMF values of x and you get the PMF value of y at y1. Similarly with y2 and so on, okay? And you observe y1, y2, etc. These are g of x1, g of x2, etc. For some x1, some x2. These will be the relationships. And when you actually arrange these, it will be g of x1 times the PMF of x evaluates as x1 plus g of x2 times PMF of x evaluates as x2, etc. All these products. And then when you write it in a compact form, you get expected value of y, which is expected value of g of x. Very similar to expectation itself. Instead of x values here, we see the g function evaluated at all those x values. Okay. And as I said, we can generalize this to a continuous distribution by, again, first considering the discretization of this continuous distribution and then taking the limit as h goes to 0. Here, you see the probability of the random variable x being in the vicinity of x sub I. It will be represented by this here, right? The PDF of x evaluated at x sub I multiplied by h. But the event that the random variable is in the vicinity of x sub I is equivalent to the event that random variable y, which is defined as the g function applied to random variable x, okay? That event, x being in the vicinity of x sub I, is equivalent to the event that random variable y is in the vicinity of the value y sub I, okay? So x sub I applied to g, you get y sub I. So that means the event that random variable x is in the vicinity of x sub I is equivalent to the event random variable y is in the vicinity of y sub I. Therefore, we can write the PDF of y evaluated at y sub I times h sub I, this small interval here, which defines the probability of y being in the vicinity of y sub I, should be at the limit equal to the probability that random variable x is in the vicinity of x sub I, which is represented by the PDF of x evaluated at x sub I times h, this small interval. Okay, so when you write the expectation of y by definition, we will have these small intervals here, okay? And each outcome value, y sub i's, multiplied by the probabilities of random variable y being in the vicinity of that value. And as I said, this can be exchanged with this due to this observation. And then what you get is, instead of yi, write just write g of x sub I, and therefore what you get is this. And when you take the limit, as you see, this will go to the integration of this PDF function, which is multiplied by g of x. So this is what you get. Expectation of any function of a random variable x, so the expected value of g of x, can be obtained by g of x times the PDF of x integrated on the entire real line. Okay, so you see, this is also valid for discrete random variables when you consider the PMF as a special case of the PDF using impulses. And this is also consistent with our definition of moments of a random variable. If you see x to the power n as a function of random variable x, this is what you get as this relation implies. Okay, g of x is x to the power n. Therefore, what you get here as the nth moment of x, you get the integral over the entire real line, x to the power n multiplied by the PDF integrated. Okay, and based on this observation, we can derive the linearity properties of the expected value. For some real number a, you get expected value of x plus a. Instead of x plus a in the computation of the expectation here, you just apply the function to every index k. So you get k plus a here. Separate this, expand this expression. So this is k times the PMF plus a times the PMF. I can pull a out of the summation because it is constant. It doesn't depend on k. So this summation is 1. Therefore, this I have a, and this here is just the expected value. So you get expected value of x plus a as expected, as we have seen earlier. Or if you scale the random variable x by a multiplier a, you just, to compute that, instead of k times the PMF, you get a times k times the PMF. And as a is constant, I can pull it out of the summation. And what remains here is the expectation. So this is equal to a times the expected value of x.